In this lecture, we will be discussing about the virtual memory. So basically, in the previous cases, we have seen like how we can do the cache mapping and how we can do the cache replacement. So these policies we have seen. So next we will see is the virtual memory. So the role of virtual memory comes when a particular process is there. If that particular process is greater in size so that it is not able to accommodate into the main memory, then we will be requiring the virtual memory basically. So in the processing, the structure basically look like this is the CPU, then there comes the cache memory, then we are having the main memory or like RAM, and it is associated next one is the hard drive, so suppose a process is there, or suppose there are three different processes P1, P2 and P3. So the process means an application that is going to be run on the computer. So in that case, these processes that will be initially stored into the hard drive will be fetched and stored into the RAM because it is going to be executed. So suppose this RAM is of only 4 KB. For an example we are considering. So suppose it is only of 4 KB and our process that is one is 2 KB, another one is 2 KB and next one is 2 KB. So because if we want to access like P1 then P2 and then P3, then if we are considering P1 it will be 2 KB stored into the RAM. Next one is P2, it can be stored into the RAM. Next in terms of P3, once we are going to store the P3 because the RAM is full, it has to remove this any of the program or any of the process so that P3 can be accommodated. Okay, but to have an accommodation to different or large number of processes, what basically used is some portion of this hard drive is taken as the virtual memory. So few portions will be taken as virtual memory. So instead of loading all these processes, because all these processes we can't load because it is only of 4K, then what we has to do is we need to make sure we will be dividing these processes into different pages. So this is a process, we will be dividing this process P1 into different pages. Similarly, the process 2 and process 3 we can divide it into different pages. So instead of transferring whole the process into the RAM, we will be transferring few pages of each process into the RAM so that we can accommodate large number of processes at the same time into the RAM. These are like different pages, and all the processes are stored into here into the hard drive. When it is to be fetched, we will be fetching few pages of a particular process. So suppose there are different processes P1, P2, P3. So we will fetch few page into the RAM. Few page of P1, few page of P2 and few page of P3. Instead of fetching or instead of storing all the process, the whole process of 2 KB, we will be taking few pages and storing into this RAM. Now all the processes are having some amount of data of all the processes are stored into this RAM. So whenever the processor wants to fetch the data, fetch a particular page, or fetch particular data from a particular page, they can do that because few pages are available into the uh, RAM. Okay, so now the all the processes can be uh, executed at the same time by the processor. So this is the basic concept of virtual memory. So virtual memory is a part of the hard drive itself, the secondary memory that we basically use, and here all the codes and data are stored. So all these processes are here, it will be storing into the hard drive only, that is virtual memory. So whenever the whenever the CPU or the processor wants to fetch a particular data of a particular process, it will be asking from the cache, and then it will be taking it from the RAM, and in the RAM some pages will be stored. So the basic concept of virtual memory came to accommodate most of the processes, even if its size is larger, so that the processor can execute the large processes also. So we can write like size of process greater than the main memory can be executed by the processor with the help of it can be executed with the help of virtual memory. So how we can basically uh, divide these large processes into different pages, and we can store into the main memory, that we will see basically in this session. Okay, so before going with the virtual memory, we will just see like how the paging is going to be work. Okay, so how the paging works, we will see that. So you can just see here. So if a processor is there, so processor basically generates virtual addresses. Virtual addresses means, if because cache memory is a physical memory, main memory is a physical memory. Okay, so whenever any address related to main memory is there, that address will be called the physical address. Any address related to cache memory will be considered as the physical address. But the processor is basically going to generate the virtual address, that is not the same as the physical address. So in between the virtual address and physical address, there is a need of a memory management unit. Basically this converts a virtual address to the physical address, or it basically maps the virtual address with the physical address, so that the data from a particular location of the physical address can be sent to the processor. So this is memory management unit. In terms of uh, virtual memory and physical memory address translation, you could just see. So this is like a virtual address will be there. These virtual addresses will be indicating to a particular physical memory. So that translation will be done with the help of MMU. Okay, you can take an example here. So basically the logical address or the virtual address is there, that we can call it like logical address will be there. So this logical address will be divided into different parts. So some part will be like, it will be indicating to a page number, and then the second part will be like the relative address within the page, or we can call it like page offset. So it will be like page offset. First few bits will be indicating the page number, last few bits will be indicating the page offset. Similarly in the uh, physical address, there will be divided into like frame number and relative address within the frame, or we will call it like frame offset. So inside this main memory, each block here, it will be indicating as a frame. So this is the frame number 13, frame number 14, frame number 15, 16, and similarly. So these are like frame numbers. So previously in the mapping case, we have seen like each memory element inside the main memory is being considered as the block. But in case of the paging concept or the virtual memory concept, we will be considering it as a frame number. Okay, so each memory element of the main memory is being considered as the frame number. It is having different frames. Okay, and inside different frames, based on the size of the data, it will be having different frame offsets. So 30 is considered as the offset. Okay, so like in this particular frame, which location of the byte or which location of the word we need to access, that is indicated by the frame offset, similar to the block offset that we have seen. Okay, and the relation between the logical address and physical address is being given by a page table. We are having a page table. Okay, so the relation between logical address and physical address is being given by the page table. So each process will be having its page table. So it is process 1 or process A is there. So process A is having a page table. In that, with respect to a logical address, this will be generated by the CPU. So CPU will be generating, the CPU or the processor will be generating this logical address. With respect to this logical address, this will be the page number. So inside this page table, basically there is, with respect to each page number, with respect to these are like page numbers, and each page number will be containing a frame number. Because to find out the physical address, we need to have the frame number and the relative address within the frame, or that is frame offset. So here page offset and frame offset is always the same. Similar to the previous, in the mapping case, we have seen like the line offset and block offset, both were same. So similar to that, here page offset and frame offset will be the same. So we are basically going to have like a page is there, and this is the main memory. So the CPU will be generating the address, that will be the logical address. It will be related to the page number, and with respect to this page number, where this page number, it will be calling for this page number. Like the CPU wants the page number 1 of process A, then this page number should be like add this page number where it is stored. So all the pages will be stored into the main memory itself. So in the main memory, at which frame number this page is there, that will be given by the page table. So in the page table, there will be a page number. This page number is located at what frame number? This indicates the frame number. So page 1 is located at page number frame number 13. Then into this frame number 13, it will be going. So to the physical address page number 13, whatever is the offset, so the page offset and frame offset will be same. So at this offset value, it will be going and finding out the page 1. So page 1 will be located where? It will be located at frame number 13. Okay, having the frame offset this 30. So this is how the processor works in case of the virtual memory. So we will further see like how we can do the paging. So is basically the paging is divided into like single level paging and multi-level paging. So we will see one by one what is a single level paging and multi-level paging. So as we will be moving, so sometimes is like always, it is always like the pages that are there, the pages are stored into the main memory. So these pages are stored into the main memory. So if the size of main memory is suppose the size of main memory is suppose 16 KB, and the size of page, so complete size of page is suppose 4 KB. So in this case, we are, if because all the pages will be stored into the main memory itself, that means into the RAM only. Then here, if the main memory or the RAM is of 16 KB and page size is 4 KB, then this page can be accommodated because the page is size of the page is less than the size of the main memory. So this will be the case of single level paging because this page can be accommodated into the RAM. So it will be the case of single level paging. Next one is multi-level paging. So suppose is the case is we are having the main memory with 16 KB size, and we are having the page, and the page is having the larger size. Okay, so suppose it is of 32 KB. So page size is 32 KB. So here 32 KB is greater than the 16 KB. So this page cannot be accommodated here. This page cannot be accommodated here into the main memory. So what we need to do? We need to divide this page into some smaller page numbers. So the size of this will be now, instead of suppose this is there, so we will be dividing it. Suppose this is of 4 KB and 8 4 KB, 8 size of 4 KB, 8 different pages being converted. So the complete page was converted to 8 different pages, and each is having the size of 4 KB. Now this can be accommodated here because it is less than 16 KB. So if the size of the page is larger than the main memory, then we will be dividing this page further. So once we are dividing this page further, we will be going to store this into the main memory now. So this dividing the page into the smaller pages will be considered as the multi-level paging. Even this page is there and page table, so there is a page and page table. So in case of the multi-level paging, basically we store the page table as well as the pages also. Okay, so inside this main memory, so inside this page table size is going to be large. If whatever we are considering here, this is basically the page table. So if our page table itself is lesser than, so it is like page table, size of the page table, and similarly the size of page table here is the, so we have seen previously like what is page table. So first of all, we are going to divide the process into, we are going to divide a process into different pages. Each page is having a particular size, and that page will also be in the RAM, that is main memory, and also along with this page, the page table will also be into the RAM only. So we were talking about here is like the page table is there, the size of page table is less than the main memory size, then it will be a single level paging we will be studying. Next one is if the size of the page table is large, then we will be converting it into different pages. So this page table is converted into different pages, so it will be like pages, page 0, page 1, page 2, and so on. So for this there will be a separate page table, this is called outer page table. At that time, this will be called as the inner page table. So we will see that later into a more description, but the basic idea we just wanted to know, like in single level paging, the size of the page table is smaller than the main memory size, then it will be we will be having only single level paging. But if the size of the page table is going to be larger than the main memory size, then we will be requiring the multi-level paging. So we will start with the basic paging concept, like what is the basic paging. So single level paging. So in single level paging, we will be coming to know like this is the main memory. So main memory will be divided into different sections. So these different sections will be like, it will be divided into different, these are like called like frames. So this is the frame 0, this is frame 1, frame 2, frame 3, and so on. If suppose and each frame will be storing certain bytes. Okay, so either certain bytes we can call it, or certain words we can call it. Like in the previous case, in the mapping case, we have seen the main memory is divided into different blocks. Each block is storing different words. Different words can be either, if it is word addressable, it will be storing the words, or if it is byte addressable, it will be storing different bytes. Okay, so for a simplicity, we are just, even we can consider that also word or byte. So suppose this is having the storing the byte. Okay, so we will be storing the bytes, like suppose one frame is storing 4 bytes, so it is like 0, 1, 2, 3. Then frame 1 will be storing 4, 5, 6, and 7. Frame 2 will be storing 8, 9, 10, 11. These are the byte numbers that it will be storing basically. So the main memory will be having an physical address. Okay, so main memory will be having a physical address. So for an example, we are considering that like the main memory size is suppose 64 byte. If the main memory size is 64 byte and each frame is storing 4 byte, so you can call it like the frame size is 4 byte. So whenever capital B is written, it is considered as the byte. If small b is written, it will be like bit. Okay, so you can consider that also. Okay, so here, so we are considering main memory that is having a 64 byte, and it is having different frames. Each frame is storing 4 byte. Each frame is storing 4 byte. So the number of frames will be 64 byte divided by the size of each frame. So it is 4 byte. So byte byte is cancel, 16. That means 16 frames will be there into this main memory. So frames starting with 0 to last one will be frame 15. So total there will be 16 frames. So this is basically the frame number. This is the frame number, and these are like, what is this? These are the bytes. So 0 byte, 1 byte, 2 byte, 3 byte. So these are the bytes that are being stored at frame number 0. Okay, so this is the main memory. Next we will be considering like a process. Suppose a process is there. So always the process is, because we are considering the single level paging, so we are considering like the process is having the smaller size. Okay, so the size of the process, so for simplicity considering 16 byte is the size of the process. So 16 byte is the process size. And also one you need to consider like whatever, each process will be having some pages. So it will be like page 0, page 1, page 2, page 3 similarly. But each page will be having the same number of bytes that are the frame numbers. Okay, so here the page size will be the same as the frame size, that will be equals to 4 byte. It can be considered similar to the mapping concept. It's like we were dividing the cache memory into different lines, and each line is having the same size as the block size in the main memory when we were doing the cache mapping. Similar way, if we are going to convert a process in the sense like an application is there that to be loaded into the main memory, so it is of size 16 byte. So if it is having the 16 byte size, and each it will be divided into different pages, and each page is storing the 4 byte the same as the frame size, then the number of pages will be the 16 byte divided by 4 bytes byte, so 4 pages. So 4 pages will be like p0, p1, p2 and p3, and each page will be having the 4 bytes. So starting with like 0, 1, 2, 3. Next page 1 will be storing like byte number 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Like total 16 bytes it can store. This is the process size. A process is there, it is having a size of 16 byte, and a main memory is there that is having the size of 64 byte. So I hope you have got the point. So this is how we basically convert. Okay, so always we should be taking care like the size of the page and the size of the frame should be equal always. So it is, we can write like it is always equal. Next we will consider is like, so we will see, so suppose a CPU is there, it is asking for a byte number suppose the CPU is asking for byte number 9, so it will be asking for byte number 9, so it will be generating a logical address. It will be generating a logical address. So that logical address will be mapped with the physical address, and that will be done by the MMU, that is memory management unit. It will be doing this logical address and physical address mapping. With respect to this physical address mapping, it will be getting the data. So from this physical address memory, it will be basically going to the main memory, and from there the data will be copied and then it will be taken back to the processor basically. So this is how is basically done. So here in memory management unit, basically it uses page table to provide the physical address with the help of logical address. Okay, so there should be a page table. So there will be a page table. So the mapping between the logical address and physical address is being done by the page table by the MMU. Okay, so what is the page table? So basically, with the help of the previous case we have seen here, the size of the process and size of the main memory is there. So with respect to that, there will be a page table. So page table, what it will be constituting is basically the page table will be having here, it will be having the page number. So if the process is having, for it will be having the page table for each process. Suppose the example that we have seen is this is the process number 1. P1 is the process number 1, suppose. So it is the page table of process 1. So for process 1, how many pages are there? So there are 4 pages that we have taken the example P0, small p0, P1, P2 and P3. So inside this page table there will be a page number with respect to each page. In the page table there will be different, the size of the page table will be like, it will be having the same number of pages that a process is having. If a process is having 32 pages, the page table of that process will be having 32 pages. But for our example, the pages in the P1 process were only 4, so the page table will be having 4 pages, and each page will be having the frame number. So here it will be like storing the frame number. That means what is the frame number is like, because it is doing the mapping between the logical address to the physical address. So it is going to store like the page number 0 is located at what frame number inside the main memory. So along with this frame number, there are some other bits are also there, but we are just focusing only on the address mapping part of, okay. So we are not considering that, like there will be some valid bits and some control bits are there that are also available in this uh, page table, but we are only focusing on the page number and frame number, okay, because we need to do the address mapping. So this P0 is the uh, page of the process, okay, P1. So we want to, because in the logical address that is being generated, the logical address that is being generated will be storing a page number and a page offset, and that to be mapped with the physical address with respect to the frame number and the frame offset. So we have not seen that, okay. So in terms of the addressing, we will just take like how the logical address is there and how the, yes, we will see the logical address. So logical address will be having the area, it will be divided into two different parts. So because logical address is there, so it will be having the, because it is about, logical address will be about the page of a particular process, so it is like page offset, or we will be calling it like it is a page offset, or it will be basically indicating the page size, okay, or the size of. So here in this case the size of the page is 4, that means it is, each page is storing 4 bytes. So if 4 bytes are there, then how many bits will be required? So here basically we need to write like how many bits will be able to indicate the 4 bytes. So there will be 2 bytes, 2 bits will be sufficient, because 2 to the power 2 we will be doing, so that will be 4. So 4 bytes it can store. So 2 bit is sufficient to indicate the location of 4 bytes. So the page offset will be of 2 bit. Similarly, the next one is like, next will be the page number. So next few bits are the MSB bits will be indicating the page number. So the logical address will be having the page offset, along with that it will be having the page number. So how this page number will be indicated? Yes, so in terms of that, the page number will be indicated by the, here first of all, process is there, process size is 16 byte, okay. So 16 byte is there, So for 16 byte, for representing 16 byte, how many bits will be required? So we have already seen like 16 byte is there, that means 16 cross 8 is there. So the size is like 16 cross 8. So if we want to find out like how many address lines will be required to address this, so it will be like we will be only focusing on 16. So this is because 8 is the one that is we are taking. Okay, so because we need to indicate it, so it will be like 2 to the power 4. So 2 to the power 4 will be equals to 16. It means 4 lines will be required, or address lines will be required. That means the address size of this process having 16 byte size will be 4 bit. So 4 bit will be able to indicate the address. So the logical address will be of 4 bit. So total will be 4 bit, and 2 bit is for page offset or size of the page. Then the remaining 2 bit will be for the page number. So 2 bit will be sufficient to indicate the page number. Okay, so here the CPU is asking for the page number, that is 9. So 9 is there. Okay, so we can store the 9. So you can just see from here where, yes, this is the 9. So you can just see here. So the 9 is at page number 2. At page number 2 the 9 is there with the offset value is like indexing. So indexing, like this will be the index value 0, this is index value 1, this is index value 2, and this is 3. So whenever the offset we are talking about, so it is 9 is stored at index value 1 and page number 2. So the logical address will be of the form this, having page number. So page number was 2. So page number 2 with 2 bit will be writing is like 10. So 10 will be indicating the page number, because page number 2 were there for the byte number 9. And offset will be like indicating the index, at what index the 9th byte is stored. So 9th byte is stored at index number 1. So index value will be like 1 for the 9th number of byte. So it will be 1 will be 0 1. So you can just see this is the page number, this is the page offset, and overall if we do or we write in decimal, it is like 1001. It is equivalent to 9 in decimal. So it is going to indicate the 9th byte basically. So with respect to the byte that is being asked by the processor, it generates its logical address this way. Okay, so once it is going to generate the logical address this way, then once we have the logical address, with respect to that we will be able to identify, like it is going to ask for the page number 2, and at that page number 2 the offset value is 2, or offset value is of 2 bit basically. So in that case, because address will be this one, this is the logical address. With respect to that logical address, we will be having 10 will be indicating the 2. Okay, so page number 2, at particular page number 2 we will be going, and with offset value 01, so at that value it is 9. So it has been asked by the processor, but this is not the exact thing that need to be fetched, because this page number is being stored, because this is the process, but we should be checking whether this is available into the frame or any of the frame is not or not. So that will be done with respect to the page table. So suppose page table is there, so with respect to each page table it will be indicating like at what particular location these pages are stored. So inside this frame, suppose P0 is stored at frame number 0, and P1 is stored at frame number 2. Similarly we can proceed further like 11, 12, 13, 14, 15, 16, 17, 18, 19. So suppose this is the frame number 0, 1, 2, 3, this is 4, this is 5 is 20, 21, 22, 23. So for an example, we are considering like the page number P0 is stored at F0 location and P1 is stored at F2 location and P3 is stored, P2 is stored is suppose at F4. So this is P2 page number of the process is stored at F4, frame number 4. Similarly, the P3 is stored at F5. So if this is the stored, this particular page will be stored into, because we have done like in paging, we are going to convert the process into different pages, and instead of instead of storing complete page, a complete process into the RAM, we will be taking some pages and we will be storing few pages into the RAM. So for an example, we are considering like the page number 0 is stored at F frame number 0 of the main memory. Similarly, P1 is stored at F2. So P2 is stored at F4. P3 is stored at F5. So this information, like at what particular frame number these pages are stored, that will be given by the page table. So into the page table, it will be indicating like page number 0 is stored at frame number 0. Page number 1 is stored at frame number 2. So it is stored at frame number 2. Page number 2 is stored at frame number 4. It is stored at frame number 4. Page number 3 is stored at frame number 5. Okay. So whenever the logical address to physical address need to be converted, it will be asking for the page table with respect to logical address. So logical address is 1001 for the 9th byte, for the byte number 9. So this is the logical address. With respect to this logical address, it is saying like this is the page number 2. We need to move to page number 2, and this is like the byte number 1. So in page number 2, byte number 1. But this page number 2, where it is stored into the main memory, we need to see by this page table. So into this page table, frame number 2, page number 2 is stored at frame number 4. So we need to move now to the frame number 4. So we need to move to the frame number 4, and at the frame number 4 we need to go with the index value 1. So index value 1. So at page number 4 or frame number 4, the index value 1 is 17. So that means at this 17th byte location, the 9th byte of the page number 2 is stored. This is how the mapping is done. So we will just indicate this is the logical address. Similarly, we will talk about the physical address, like how the physical address is basically given. So physical address, so the size of physical address, so first of all, the physical address will be of like two part will be there. So this will be like the frame offset, or it will be regarding the frame size, and this will be the frame number. So based on the size, so it is of 64 byte. So if it is 64 byte, how many bits will be required to indicate? So address bits for 64 byte location is like, so it will be like 64 cross 8. So only this will be indicating the number of address lines. So 64 is there, that means it will be indicating like 6. 2 to the power 6 we will be doing. Okay. So 2 to the power 6 will be equals to 64. So we can say like 6 bits will be sufficient to indicate all the location or the frame numbers, because it is like complete bit, different 64 bytes are there, so each byte can be indicated with respect to 6 bit. So physical address will be of 6 bits. So into the 6 bits, the page offset and frame offset should be of same size, so it is of 2 bit, so it will be of 2 bit. The next one is like this frame number will be indicated by the 6 minus 4, 2. 6 minus 2, that is 4. So 4 bit. So frame number will be indicated by the 4 bit. So now how this physical address is being generated is like, so physical address will be like, so with respect to this logical address, it is 2 written means it is indicating the page number, and this 2 is means the byte. This is sorry. This is 10 is there. Logical address will be this one. So it is of 10. That means page number 2 is it is talking about. 01 is there. 01 means it is talking about byte number 1. Now we need to go to page table and search for page number 2. So into the page table, page number 2 is there located at frame number 4. If it is located at frame number 4, that means into the physical address we will be going to page number 4. Okay, so page number 4 we will be going with the offset value 01. So 01 will be the offset value in the frame offset, and it will be going to frame number 4. So 4 we need to represent in terms of 4 bit, because the frame number will be indicated by 4 bit. So it is going to be indicated to the frame number 4. So frame number 4 can be indicated in binary as like 0 1 0 0. So 0 1 0 0 will be the frame number 4. So now with respect to this frame number address, we will be moving to that frame number, and at that frame number we will be going to index value 1. Okay, so that will be this will 17th location byte will be having the 9 location of the page. Okay, so with respect to that we will be finding out. So if we combine it like 0 1 0 0 0 1, so this is the binary bit of the physical address. If we convert it into equivalent decimal, it will be like 8 16 plus 1 17. 17, that means 17th byte number location into the main memory will be storing what the processor wants. So you can just see from there, it is the 17th byte location that is going to have the 9th byte location of the page number 2. That is the processor wants the 9. So I hope you have got the point, like how we will be basically going to convert of logical address to the physical address with the help of a page table. So with respect to each process, there is a page table. If there are 3 processes, there will be different page table P1, P2, P3. For process 1, process 2, process 3, there will be 3 different page number, and each process will be having page number starting with P0, P1, P2, P3 and so on. Okay, so similarly page number 2 will be having process number 2 will be having the same page number 02. Whatever the size will be there of the process, there will be the page number. So page number will be defined by the page process size. So this is the single level paging that we can conclude with. The next we will see is the multi-level paging. So in the multi-level paging, you just have to get the basic. There will be some sort of confusion type also, so we will be letting you know like how we can proceed further.